Ever wonder why your video calls freeze but your downloads never do? It's all about QoS quality of service. Without it, voice calls lag, video buffers, and your network slows to a crawl. But with QoS, you can control which data moves first, keeping your calls clear, your video smooth, and your downloads fast. Want to master QoS and take control of your network traffic? In this video, you'll learn how to prioritize calls, video, and data to avoid lag, reduce packet loss, and ensure a seamless connection every time. Don't miss out. Your path to mastering QoS starts now. The principles of QoS. Network devices don't really care what kind of traffic they need to transmit. In the basic operation of a switch, when it receives an Ethernet frame, it looks up the destination MAC address, and it will forward the frame to that destination. In the case of a router, the principle is identical. That is, when it receives an IP packet, it looks up the destination IP address in its routing table, and will send the packet to the destination. The router or the switch make no difference between a frame or a packet, whether it is intended to download a video or to communicate with a VoIP telephone. This mode of operation is called best effort, or FIFO, first in, first out, which meaning first come, first served. This type of default logic can sometimes be problematic. For example, on this topology, we have a small network consisting of 2 routers, 2 switches, 2 PC, and 2 IP phones. The links are all in gigabit Ethernet, except between the 2 routers, where we have a very slow serial link. That is to say, only 1.54 megabits per second. When the PC and the IP phone, on the left, transmit data and voice packets intended for the devices on the right, well, it is very likely that the serial link is congested and that the router places the packets in queues. The problem with this is that a router's queue isn't unlimited. And what should the router do when its queue is full? Well, the packages will probably be deleted. So, when it comes to PC data packets, this is not necessarily a problem, as users will only complain about poor transfer speed. On the other hand, when it comes to voice packets, well, users will complain that they don't understand their interlocutors. QoS is the use of tools to change the way the router or switch handles different packets. For example, we can configure the router so that voice traffic is prioritized before data traffic. QoS can be used to process 4 types of network traffic. We have the bandwidth, jitter, delay, and packet loss. With QoS, we can change the priority of certain types of traffic. The configuration of the QoS will depend mainly on the applications that will be used. That's why we're going to take a closer look at the different applications and types of traffic. For the first example, we will take a user who wants to download a file from the internet. For example, the version of Packet Tracer on the Netacad website. The 64-bit Windows version is 146 megabytes. We'll see how bandwidth, delay, jitter, and loss are important to download a file that looks as basic as this one. The 64-bit Windows version is exactly 146 megabyte, or 154,019,600 bytes. An IP packet is 1,500 bytes by default. Subtracting the IP and TCP headers, which total 40 bytes, leaves 1460 bytes for the TCP segment. So, in your opinion, how many IP packets would it take to transfer this file to his computer? For this, subtract 154,019,600 by 1,460. This gives about 105,492 IP packets. The higher the bandwidth, the less time you will have to wait to receive the file. Between the Netacad server, where the Packet Tracer software is located, and the PC, there is a delay that is called unidirectional. When you click on the download link, all you have to do is wait for it to finish. There is no longer any interaction between us and the download. Packages arrive quietly, no matter how late it changes, which is called jitter between packets. File transfers like this one use the TCP protocol. And when some packets are lost, then TCP will retransmit the data, making sure that the download arrives completely on the computer. A web browser that downloads a file is a non-interactive application, which can also be called a batch application. The bandwidth is nice to have, as it reduces the time it takes to wait for the download to complete. Delay, jitter, and loss are not critical. That is to say, they don't matter. With QoS, we can allocate enough bandwidth to applications like these to ensure that downloads complete on time and thus minimize packet loss to avoid retransmissions. Another type of application is the interactive application. This is the type of application that is found when you use Telnet or SSH to connect to your router or switch. These types of applications don't require a lot of bandwidth, but they are still quite susceptible to delay and packet loss. Imagine having to wait a certain amount of time between each order placed on a switch or router, or even in case of a strong disturbance, that there is a short pause between each character you type. It can get very annoying in the middle of a setup. Well, with QoS, we can ensure that in the event of congestion, interactive applications are served first, ahead of batch applications, which are very bandwidth intensive. Voice and video applications are the most difficult applications that you can manage on your network because they are very sensitive, delay, jitter, and packet loss. In the example, we have a user talking with his IP phone. VoIP uses a codec that processes analog sound into a digital signal. Analog sound is digitized for a certain period of time, which is usually 20 milliseconds. With the G711 codec, every 20 milliseconds of audio corresponds to 160 bytes of data. The phone will create an IP packet with a UDP and RTP real-time transport protocol header, adding voice data to it before transferring it to its destination. The IP, UDP, and RTP headers add an additional 40 bytes to the packet, resulting in a total of 200 bytes. This means that for 1 second of audio, the phone will create 50 IP packets, and 50 IP packets times 200 bytes equals 10,000 bytes per second. This is equivalent to 80 kbps. The G729 codec allows you to use less bandwidth. For 1 second, it comes down to 24 kbps. On the other hand, the audio quality is reduced. Bandwidth is not really a problem for VoIP, its real problem is on the delay. Because if you're talking to someone on the phone, it's usually in real time. And if the delay is too high, then the conversation will become a bit like a walkie-talkie conversation. That is, the kind of conversation where you have to wait a few seconds before you get a response. Jitter is also a problem, as the codec waits to receive a certain number of IP packets so that it can convert them back into an analog signal. And packet loss is also a big problem. It's not very pleasant to communicate with a person if the conversation is missing several words. So, despite all these problems, voice traffic over a data network is still possible, but QoS will be required to ensure that there is enough bandwidth and to control delay, jitter, and packet loss. And here are recommended limits that should not be exceeded. One-way delay, less than 150 milliseconds. Jitter, less than 30 milliseconds. Loss, less than 1%. As for video traffic, it has similar requirements to voice traffic. It still requires more bandwidth than voice traffic, but it really depends on the codec and the type of video being streamed. For example, if I'm recording a video where I'm setting up a router, Well, since most of the screen remains fixed, it will require less bandwidth than a sports video. As with voice traffic, video traffic is also susceptible to delays, jitter, and packet loss. And here are the recommendations not to exceed for video. One-way delay, 200 to 400 milliseconds. Jitter, 30 to 50 milliseconds. Loss, 0.1% to 1%. We've talked a little bit about why we need QoS and the different types of applications that have different requirements. We will now quickly discuss the tools to use to implement QoS. Classification and marking allows you to identify and mark packages so that they can be treated differently. We have a queue and congestion management. That is to say that instead of having a large queue where packets will be processed with the FIFO, first in, first out, mechanism, it is possible to create several queues with different priorities. Shaping and policing are used to limit traffic. And there is congestion avoidance, which allows you to manage packet loss and reduce congestion.